Hi, this is the first lecture in orthopedic trauma. We're going to discuss general principles. A good source that you can use for studying orthopedic for your final exam is this book written by myself. So this speaks about biomechanics of the plate. There is two types of plate construct that I'd like to discuss with you, the locked screw and the non-locked screw. Let's start with the locked screw. We have these two pictures here. They're from the AO website. First, let's start with the locked screw construct. The locked screw is a screw that has threads into the head. These head, as you can see here, these threads are in the head, and these threads thread into the hole in the plate and become a fixed angle. So this screw here will lock here into the plate, and it will not move in relation to the plate. So it will not move into any direction. On the other hand, here, as we're going to speak, the non-locked screw construct, this screw does not have screw head does not have threads, it does not thread into the hole, and it does not have a fixed angle, so it can move a few degrees in any direction in relation to the plate. It can go this way, or in the other plane it can go also other ways. So it does not have a fixed angle to the plate. Of course, it does not move in real life if there is good purchase into the bone, but if there is no good purchase, it can move. Or if this screw, before you put the plate in the bone, if you just put the screws into the hole, you'll be able to see how much motion you can get of the screw in relation to the plate. This does not happen here because these threads here will lock into the plate. It becomes a fixed construct. Because the screw will lock into the plate, it will not push the plate towards the bone. So if this plate is not adherent to the bone, the screw will not push it further towards the bone. So if you see here, as we're going to discuss when we go to the non-locked screw construct, the screw will thread into the bone and push the plate to the bone. Here it does not do this, and because it does not push the plate towards the bone, it cannot be used as a template of reduction. So let's say that you have a straight bone, for example, mid-shaft humerus. If you use a locked plate construct and the bone is not reduced before you put the plate will not reduce the bone for you because it does not pull the bone towards the plate. So it will keep the same relation before putting the screw and after putting the screw. So let's see how this how the locked screw construct will fail. So in general, this is like a non-locked screw construct, as we're going to say. When if the plate starts to move away from the bone, it will happen sequential. So it starts with this screw, and then this screw, and this screw. And because the screws does not have a fixed angle, they can just come up. If you notice here, this angle is different than this angle is different than this angle here, because the screw can become in a different angle here. So this is like a 90 degree, this is not a 90 degree, so the screw can just go up. It does not have to take too much bone, and it goes sequential. So it starts with this one, and then this one will go, and then this one will go. This is different than this here. So as we said, this is a fixed angle. In most cases, it's 90 degree. It does not have to be 90 degree, but in most cases, it's 90 degree, and it does not come one after the other. It just, the whole plate will come as a single unit. That's why it's called catastrophic. It's not sequential as here. Here it is catastrophic. All the screws fail in the same time, and because we said it keeps the same degree, 90 degree, it will not come up like this straight, because if it comes up straight, that's a different angle than 90. It will stay 90 degree, and it will take relatively more amount of bone. So do you see here, it takes much more amount of bone than it takes here. So that's why it's called catastrophic failure. So what are the indications of using locking plate? The most important indication for using locking plate is metaphyseal comminuted fracture in osteoporotic patient. So if you see like this patient is an 80-year-old with rheumatoid arthritis on steroids, she has severe osteoporosis, she has a metaphyseal upper tibial fracture, it's highly comminuted. This fracture actually was treated in the beginning with nail, and it failed the fixation. So it had this fixation, which is locked plate. If you see, all the screws here are locked. Whether the proximal group of screws here or the distal group, all of them are locking screws. So the most important indication is comminuted metaphyseal fracture in osteoporotic patient. The use of locking screws can allow better fixation in these cases. Another indication for using the locking plate in periprosthetic fracture, if you see here is the periprosthetic fracture, as we're going to discuss these fractures in details in the cases of, in the chapters of total hip arthroplasty, periprosthetic fracture. But in general, you need to put fixation here in this part. You cannot use bicortical screw because the stem of the total hip here is into the medulla. So in this case, we use here a locking plate. If you see the two screws proximally here are locking screws unicortical. Another indication is the bridge plate. Actually, bridge plating can be done both by locking or non-locking. However, if you think that the plate is not lying onto the bone, you can use it in this case as an internal external fixator and use a locking screw. Like in this case, the plate is not touching the bone in this area, and if you want to add more fixation, you can use a locking screw which will lock into the plate and have purchase in the bone. It does not have to push the plate towards the bone to get fixation in these cases. So bridging fixation, as this is like a submuscular bridge plating in a femur fracture in adolescent patient. Again, the bridge plate can be locked or non-locked. However, if you want to use it as an external internal external fixator and have a fixed angle that the plate at this area is not touching the bone, you can use a locking screw. After we discuss the locking plate construct, let's discuss now the non-locked plate construct. These are the two pictures that we saw before. We saw here the locked construct in which the screw head has threads and the screw will lock into the plate. It will not push the plate towards the bone. Here is the non-locked plate construct. The screw head does not have thread. The hole does not have threads. The screw will get purchased into the bone and then will push the plate towards the bone. It acts by friction, pushing the plate towards the bone, so you'll get compression between the plate and the bone, and the construct here depends on friction. It's not a fixed angle as this one. This screw, when the screw is not into the bone, you can see it moves in relation, it can move in relation to the plate. It depends here on the principle of friction. The screw will gain purchase into the bone, will push the plate towards the bone, as we said, and you will have friction here between the plate and the bone. As we said, it will pull the bone towards the plate, so you can use now the plate as a reduction tool because the bone will come towards the plate, so the plate can be used as a reduction tool in these cases. We also explained that concept of failure. The screw here does not have a fixed relation to the plate. So if you see here, this screw has a different angle to the plate than this screw. So when the failure starts to happen, it happens a screw after another. It does not happen all the screws together as in the locked plate. So the failure here is sequential. So every screw will fail and then it will come the next screw. Because the screw can move its angle or can change its angle from the plate, it can go up from the bone directly. It does not have to take too much bone while it's coming out. So the failure here is sequential. The screws will back up. It does not have to erode too much bone as happens in the locking plate construct. So this is the non-locked plate construct. The screw plate angle can change and the screws can come directly outward and they are sequential mode of failure. So this speaks about the hybrid locking and non-locking fixation. You can use that. You can use combination of locking and non-locking screw. However, we start first with the regular non-locking screw, as you can see. So this is a bridging plate, the plate that we saw in the example before. It's a submuscular bridge plating in an adolescent femur. First, after we introduce the plate, there is a gap between the plate and the bone. So we use a regular screw of non-locking screw above and non-locking screw below. That will allow us to use the plate as a reduction tool and will allow the plate to be pushed to the bone. And then after that, if you would like to add more non-locking screw, you can. In this example, this one, the plate is away from the bone, so we use a locking screw. It does not have to work with the principle of bringing the plate to the bone, because it will lock into the plate. So whenever you'd like to use a hybrid, you first start with a regular non-locking screw, and then you use a locking screw after that. If you start with a locking screw in the beginning, the screw will lock into the plate. You will not be able to use the plate as a reduction tool, and it may prevent your reduction. So first lag, then lock. First use a non-locking screw, and then use a locking screw. After we have talked about the locked and the non-locked plate construct, let's talk about the mechanism of action of the plate when we use them for fractures. There are different mechanisms for plate functions. We're going to start with the first one, which is the compression. The plate can be used in a compression mode in cases of a fracture. In order for you to do this, one side here first to be fixed in the central hole, and then on the other side, the screw has to be applied at the peripheral part of the hole, away from the fracture. And because this hole here is slanting, when you tighten the screw, this will result in the plate moving this way and bringing the compression over the fracture. So if you can see here, the screw was tightened, and this will bring the plate and this part of the bone towards the fracture, obtaining compression. This picture is from the AO website. So again, the first mode of using the plate is in the compression mode. For you to obtain this, one screw will have to be done on one side in the central part. The other part, on the other side of the fracture, the screw has to be applied eccentrically at the peripheral part of the hole, away from the fracture. This will allow compression over the plate. Another important aspect is in order for you to obtain compression across the near and far cortex, the plate has to be pre-bent in a way that is the concavity is towards the bone. So if you don't pre-bend the plate and you obtain a compression, the compression will be applied on the near cortex with some distraction at the level of the far cortex. For you to obtain compression on both sides, pre-bending is done. Pre-bending should be done in a way that the concavity, as you see here, is towards the bone, and then with tightening you will be able to obtain compression on both the near cortex and the far cortex. Of course, with further tightening of this, the plate, this pre-bent part, will be more forming towards the bone. Two concepts. The screw has to be applied eccentrically away from the fracture. This will bring the plate construct towards the fracture, obtaining compression. To obtain compression across the near and the far cortex, the plate has to be pre-bent in a way that the concavity is towards the bone. Another important aspect when using the plate in the compression mode is the sequence of screw insertion. These three pictures are from the AO website, and it shows this concept. So let's start with this picture first. The correct way of doing this is to fix the plate first in the segment of the fracture that is actually more than 90 degrees. So first you apply this screw so that you can obtain a stable part on this area which has more than 90 degrees in the fracture segment, and then you compress with the area that has a fracture that is less than 90 degrees. We call that compression through the axilla. So you will have here a stable construct by applying this screw here, and then you can compress this part into this axilla here. So first part is you apply the screw in the fracture area that is more than 90, and then you compress into the fracture segment that is less than 90, and we call this again compression across the axilla. If you do the reverse, so if you start the screw here in the fracture that is less than 90, and then you start compression here, there will be shear forces, and there will be some shorting that happens during this process. This shows here the same thing. So you will apply the screw first into the area that has the fracture segment more than 90, and then you will compress through axilla. The difference here is that you have this butterfly segment. So you try to obtain that stable construct before compression so that you don't get shortening. The same here, so here you fix the screw and then you use this lag screw here to obtain a fracture segment that is more than 90, and then you will compress across that axilla here with the fracture segment that is less than 90. So if you see this here, this is a good example. So this is a fracture both bone forearm. This is the radius, this is the ulna. The more proximal part here is the radius. And this fracture here, which is common to see, you will see that it's going from distal volar to proximal dorsal. Here is the segment of the radius here, and this is the other segment of the radius. So when you start fixing this, in most cases we do Henry approach and we go volar. So you will fix the plate first into this segment because this has more than 90 degree, and then you will compress here into the axilla, which will be here. So you will first fix the plate towards the distal part, so that because the fracture line here is more than 90, you will have a stable axilla that you can compress through. Another common method of using or mechanism for using the plate is neutralization. In these cases, the fracture is fixed first with compression lag screw, and then the plate is applied to neutralize the forces, the shear force and the bending and rotational force. So if you see here, there is a spiral fracture of the fibula. You can see it here also. The fracture was first fixed with 2 lag screws. The lag screw will obtain the compression across the fracture, and then the plate is applied over the fracture to help neutralize the forces, the shear force, bending force and rotational force that can affect the fracture with only if we have only the compression screws. So in neutralization mode, the fracture is first fixed with compression lag screws, and then the plate is applied over that. The value of this plate in this case is to neutralize shear force, bending force and rotational forces. Another commonly used mechanism of action of the plate is a buttress plate. Buttress plate is used for partial articular fracture to prevent shear forces across the joint. So if you see, this is an X-ray of lateral tibial condyle fracture. So this is a partial articular fracture, as you can see here. And this plate is used as a buttress. What does it mean, buttress? Buttress means that the plate will be pushed tightly against the bone in this border here, and this will prevent shear forces on this segment on going this way. So this plate here, as you see, is very tightly pushed towards the bone using regular cortical non-locking screws. This will push the plate all the way to the bone and will be act now as a buttress, so it will prevent any shear forces on the partial articular fracture. So the partial articular fracture is here. When there's any forces across the joint, it will not have any shear force here because this plate is buttressing that fracture. So again, it's very important that the screws into the main segment here are not non-locking screws to push the plate all the way towards the bone so that it can buttress this fracture. A typical buttress plate does not need actually to have any screws into the articular segment. However, you can always add some screw for added fixation. But the buttress, the pure buttress plate does not need to have any screws into the proximal segment or the articular segments in general. It's commonly used for lateral condyle fractures of the tibia. Also, another commonly used is the volar parton. You can also put a plate in a buttress fashion that can or cannot, that can have fixation in the distal fragment, or it can be used only as a buttress with no fixation into the distal fragment. So buttress plate, commonly used method, it depends on the plate being pushed all the way very tight to the bone using cortical non-locking screws, and then it will resist any shear forces across the articular fracture. We have described the plate in the compression mode, in the neutralization mode, and the buttress mode. Another important mode for the plate in fracture is tension band mode. So how can the plate be a tension band mode? We're going to explain this using these pictures from the AO website. So this picture here is of a femur. The forces on the femur goes on this mechanical axis. So the medial part of the bone is under compression and the lateral part of the bone is under tension. So when you get a fracture here, mid-shaft femur, there is a compression on the medial aspect of that part and tension on the lateral aspect of this part. If you apply the plate theoretically on the medial aspect, you will still have some compression here. However, all this part here of the bone is under tension now. But if you apply the plate on the lateral aspect, this plate will be under tension force because the forces are going on this side, so there is tension on this part. However, all the bone part here is now under compression. So the plate works by converting the tension forces into compression force over the fracture side. So the plate in this area here will become under tension because there is a forces here. So this plate is under tension. However, this plate is under tension, but all the bone underneath it now is under compression. So there is a tension force here, but all this part now is under compression. So the shift between compression and tension is not in the middle of the bone or in the medulla, maybe in the middle or on the 1/3. It's by applying the plate now, you're going to shift that relation so that only the plate is under tension and everything else in the bone here is under compression. So the tension band, the idea of the tension band, it converts the tension force to compression force. How it's done? By applying the plate to the tension side of the plate. So the plate will be under tension, but all the bone underneath this plate will be under compression. There will not be any part of the bone that is under tension now. However, for this principle to work, it assumes that there is a contact in the bone. So if there is a defect, as you see here in this part, there will be a failure of this construct because there is nothing to compress here. So this bone here, this fracture will fail by going into varus because there is nothing here that is can withstand the compression forces. So using the plate in the tension band requires that the plate is applied over the tension surface, and it's now going to make all the bone under compression. It's not going to be as before, some of the bone is under compression and some of the bone is under tension, because the only part will be under tension is the plate, and then everything else will be under compression. For this principle to work, there has to be a bone contact. If there is defect, this principle will fail. Another important principle for using the plate is bridge plating. Bridge plating depends on fixing the plate to the bone proximally and distally, spanning the injury zone, which will help maintaining the fracture hematoma. Hence, sometimes it's called biological fixation. The plate is fixed proximally and distally. This is the picture that we showed before. For a submuscular bridge plating, the plate is fixed proximally and distally. As you can see here, the fracture area has been spanned. This helps maintain the fracture hematoma, which will help the healing, and that's why sometimes the bridge plating is called biological fixation. The main indication for bridge plating, if there is marked comminution of the fracture side, as this helps to avoid marked stripping of the periosteum from all the fragments. So bridge plating, the plate is fixed proximally and distally. It spans the fracture area, maintaining length, rotation, and alignment, and this helps the healing by maintaining the biology, because the fracture hematoma is not disturbed and the periosteum is not removed from the fracture ends. This is the end of the first lectures. There will be more lectures about the general aspects of trauma.